case I forgot about it. So this section here, 13.7, goes on to talk about triple integrals in Cartesian coordinates. Okay, so triple integrals. All right, folks, if you don't mind, let me try to think about the way to get this off. I mean, it's kind of like annoying, the window in the middle of the screen. Do you guys see that as well?
Yes.
Okay, let me try to. Yeah. Yep. Now it sort of leaves, comes and goes. Let me pause the share and hopefully this will go away. All right. Let's go on there. Stop share. All right. Yep. And then share. What's going on here? All right, bear with me for a minute. Close the window. Okay, how about now?
Yeah, everything.
Okay, good, right. Okay. Yeah, at least you don't see the windows. I mean, the rectangle sitting in the middle of the screen. All right, so the 13.7 triple integrals, we've learned a lot about the double integral. Now let's go further to triple integral. Our objectives is to use a triple integral, understand what's triple integral and how to use the triple integrals to find the value. Okay. First of all, let's kind of like get a introduction to triple integral. We'd like to get the idea from single integral to double integral and then further try to understand triple integral. Okay. You guys remember the notation for single integral? Yeah, it's pretty easy, right? Notation for single integral is just one integral sign. Okay, so let me go ahead and see. So integral of f of x dx, and it is over a line segment, so from A to B, right?
Mm-hmm.
Now, double integral is double integral of f of x comma y. So a function of two variables. And then you have, in general, we say dA, right? dA over region R. So you see the change from only one line segment, right? From one line segment to a region from one dimension to two dimension. And from dx, which is only measuring the length, to dA, which is measuring the differential of the area. Okay. So triple integral, we would have triple integral, still a function of two variables, f of x, y. This time, it's not just going to be dA. Okay, so from the length in one dimension to area in two dimension, what do we predict is going to happen in triple integral? So length is the idea, is the concept in one dimension, right?
Mm-hmm.
The area is the concept for two dimension. Okay. So in triple integral, we should go ahead and get to three dimension, right? Three dimension, so we should have a solid region, okay? Instead of having a flat region in two dimension, we'll have a solid region. Okay. It might be box, it might be other look. So suppose this is Q. As for a three-dimensional item, what do we measure typically?
Volume.
Yeah, volume, so be dV, okay? So you see the change from one dimension dx to two dimension differential of area to the three-dimension differential of the volume. And it's integrating over, originally is a line segment. Double integral is integrating over a two-dimensional region. and then three-dimensional, it's over a three-dimensional solid region. Okay. So that's kind of, we can guess, right? And also let's take a look at, let's sort of guess the definition, which is about limit of the Riemann sum, right? So limit of Riemann sum. And in single integral, we know this integral equals to a limit as the partition norm goes to 0 of sigma, which is the sum of all the function value at a specific point that you have selected, and then times change of x of I, right, dot xi. If you recall that in one integral, okay, one single integral. In the double integral, we go further from, still we're having a limit of partition norm going to 0, and then function value, still a sum, a function value at selected x and y's, and dA turns to delta of area, right, delta area. So lastly, if we look at the triple integral, we should expect this to have the limit as partition, the magnitude of partition going to 0, almost as small as it can be, summation of function value times the change of volume, so delta VI. Okay. We'll see this in a minute. We'll see this by using an actual graph to visualize it. Okay. But as of now, we can sort of guess from single integral to double integral. Therefore, we can sort of we can infer the definition in triple integral. Okay. All of these is for I goes from 1 to n, I goes from 1 to n, I goes from 1 to n. All right, so we've just kind of like give a very brief review, a kind of introduction of triple integral. Now let's go the evaluation, okay? The example 1, triple integral. Even though it's triple integral, the way we calculate it is the same as double integral. So in this case, integral from 0 to 5, from -2 to 4, 1 to 2, 6xy squared z cubed dx dy dz. Okay, we start from the innermost part. So 1 to 2, 6xy squared z cubed dx, right? So we should have 6y squared z cubed. They are not related to x. Only x is the variable. So 6y squared z cubed is considered to be a constant coefficient. That could be pulled to the front. Antiderivative for x would be x squared over 2. Is that good?
Yep.
Okay. And our x goes from 1 to 2. So you can simplify 6 and 2. I can get 3 here. So it's 3 y squared z cubed x squared. X goes from 1 to 2. So we can plug 2n for x and plug 1n for x for evaluation and subtract those. So we should have 3 y squared z cubed. When 2 is in, I have 4. When 1 is in, I have 1. So it's 4 minus 1, which I can say it's 3. It's 9y squared z cubed. That is the first layer. For triple integral, we just have 3 layers in total. So we just follow our previous procedure for iterative integral. So second layer goes from -2 to 4. And this red box will be 9y squared z cubed and dy. Okay. All right, over here, y is our variable. So we take 9z cubed out as the constant coefficient and then find the antiderivative y squared. So it'll be y cubed over 3. And then y runs from -2 to 4. right? So 3 and 9 could be reduced again. I have 3z cubed y cubed, y runs from -2 to 4. I'm going to go ahead and plug 4 and -2 in and subtract those two. So I have 3z cubed. When I throw the 4 in, I have 64. When I throw the -2 in, I have -2 cubed, which is -8. So that's 3z cubed times 72, which would be 216 z cubed. Right?
Yep.
Okay. And lastly, you just do lastly, you just evaluate the outmost layer. So I have 0 to 5 and 216z cubed dz. So in this case, I can do 216 z to the 4th over 4, and z goes from 0 to 5. Okay, and looks like 216 and 4 could be reduced, right? In these two, you can reduce that to 54. So you do 54 times 5 to the 4th, subtract 54 times 0. So eventually it's going to be 54 times 5 to the 4th. 25, 25, 625. So it'd be 54 times 625 is going to be the number that we have for this triple integral. Make sense?
Yeah.
Okay. Any quick shortcut for this question? I'm going to ask you guys to think about it. Is there any shortcut you can think of? Observe this question one more time. For this particular problem, okay, this particular problem, take a look at the integrand. Is the integrand separable? 6
Yes.
x y squared z cubed, it's separable, right?
Mm-hmm.
Okay. Are the limits all constants?
Yes.
Yeah, these are constant limits. So remember, for double integral, when it comes to separable integrand with constant limits, we can just separate the x with y's with the z's, right? So same thing here. Let's go ahead and separate it. So I can do this integral I would just be, the integral I will be the same as the product of 3 single integrals. Okay, one is dx, one is dy, one is for dz. And x goes from 1 to 2, y goes from -2 to 4, and z goes from 0 to 5. And I just need to separate the function. Okay, so you can separate x as 6x, and y could be y squared, and z could be just z cubed. So for this particular problem, you can also do it in this way by using the separable function. The integration could be separated into 3 single integrals. Okay, you should have the same answer towards the end. All right. Okay, so the shortcut method works for these type of integrals. Okay, so this is our first look at the triple integral. Next, let's talk about our limit of the Riemann sum, okay, the one that we have mentioned here. We said what has changed is, in the end, we're changing from the delta x, which is only measuring the length, to delta a, which measures the area, to delta v, okay, delta v. So here is one graph. Definition of triple integral. Let's look further into it. So the procedure used to define a triple integral follows the similar procedure used for double integrals. So we're consider a function f. Okay. Yep, so it can be 3 variables. Yeah, did we forget to put the z there? Yeah, so 3 variable. Gotta put the z. And that is continuous over a bounded solid region R, Q, right? So this is solid region Q, as you see here. Solid region Q. Then what we need to do, first of all, is we need to get a partition of Q, okay, partition of Q. So we need to decompose this region Q. So the way we do it is, again, we're going to take some regular shape, which will be like the box shapes. So what we do is, this is currently my Q, and I'm going to decompose it into different boxes. So a bunch of little boxes, as you can see. So decompose it into boxes. So then the volume of this Q, which is delta Q, right? Delta Q can be approximated by all of the sum of these delta V. Okay, because each little box you can calculate its volume, right? You guys okay with that? So volume
Yes.
of Q will be the sum of this delta V. And because each little one of those are boxes, their volume is easy to compute. So let's move on to the next slide. So the volume of the ith box, delta V, because it's box, the volume will be length times width times height. So delta X in the X direction, delta Y direction, and delta Z in the Z direction. So the norm magnitude of delta, which is the same as magnitude of P as some book uses. Okay, so magnitude of the partition would be the length of the longest diagonal. And eventually we're going to push this delta, magnitude of the delta or magnitude of partition going to 0. Okay. So we're going to choose a specific point in each box as the representative point. Later on, we can call them xi, yi, z sub I, okay, star. So that will give us this Riemann sum, summation of function value at those represented point times delta V, which is d3. And later on, we'll see dx, dy, dz forming. Therefore, we have the formal definition for triple integral. Okay. So if function f is continuous over a bounded solid region Q, then the triple integral of function f over the solid region Q, this is solid, is defined as triple integral of f x, y, z dv equals to the limit of pushing the magnitude going to 0 and summation of the function value times delta v. We need to get this triple integral if the limit exists, right? And later on, we will know that the volume of the solid can be evaluated by using triple integral of dv over q, which is a simpler format. We'll just talk about this just later. Okay. But as of now, this definition of a triple integral is very similar to what we originally guessed. Okay. Now, there are a lot of similar properties in terms of the operation of these integrals. The similar property goes from single integral to double integral to triple integral. Okay. So first of all, triple integral of a constant c times f of x, y, z dv, the constant c, constant coefficient can be pulled out, right? Secondly, triple integral of the sum or difference equals to sum or difference of the triple integral. You guys recall property 1 and 2, if you combine together, what do we call them? It's called the linearity property of the integrals, right? Mm-hmm. Linearity. Okay, part C. Triple integral over solid region Q equals to triple integral over region Q1 plus triple integral region Q2 if Q, okay, region Q equals Q1 union Q2. You guys recall what's the name of this property? So let's do this. So if I have a box, right, which is Q, I can decompose it into two parts. One is Q1, one is Q2. Then the integral over Q will just be integral over Q1 plus integral over Q2, right? That's actually called additive property, right, over region. We have the similar property in single integral and double integral, right?
Yep.
Mm-hmm. Okay, so in the last property, Q is the union of those two, Q1 and Q2. All right, next. If the solid region Q is simple, okay, what do we know? What do we define Q to be simple? We can just call it to be regular or rectangular. So if the region Q is rectangular, meaning X is bounded between two constants, Y is bounded between two constants, and Z is bounded between two constants. So A, B, C, D, E, F. Then this region Q is just simple, right? There's no complication for X, Y, and Z. Then for this dV, it doesn't matter how we do that. We can go dx, dy, dz, or we can do dy, dx, dz. There are 6 different ways for you to evaluate, and you should have the similar answer when the region Q is regular, rectangular, or simple. Okay. So this is kind of like similar to the one we just did in example 1. Okay, in example 1 here. We can say in this example, X is between 1, 2, Y is between -2 and 4, and Z is between 0 and 5. All of these are constant limits, so it doesn't matter whether you go dx, dy, dz, or dy, dx, dz, or dz, dy, dx. Okay, the order is interchangeable when you have constant limits, which means it's a simple region. So those are the ones that's easy to take care. But the ones that are not easy to care is the more general case, right? Which is the non-rectangular region, okay? So remember when we are talking about double integral, we have mentioned that for double integral, there's X simple and Y simple, right? If it's Cartesian, or you can do R simple, theta simple if you're using polar coordinates, right?
Yep.
So similarly for triple integral, if we're just using Cartesian, then we have X, Y, Z. So I can have X simple, Y simple, and Z simple regions. The one we use most often, okay, the one we use most often would be Z simple, actually, because that's the easy one. A lot of times this is easier. Kind of like in double integral, a lot of times we go Y simple region, right? So triple integral, a lot of times we go Z simple region. So here is the definition of how you define Z simple region. So Z simple region, first of all, Z must be bounded between two functions. Okay, so Z must be between G1 function and G2 function, and those are about X and Y's. And after that, you look at X and Y. One of them will be bounded between two constants. Suppose X is bounded between two constants, then Y would be bounded between two functions related to X. We'll see this more in our later examples. Okay, I do want to emphasize you guys see the change of variables, the change of number of variable here. So x will be bounded between constants. Y will be only related to x. And then further, okay, so y is only related to x. And further, z will be related to both x and y. So here you have x, y, x, y. We'll see more of these patterns in our later examples. And once you have these region, which is the simple region has been defined, we can go ahead and write down the triple integral. So again, the constant will be in the outside layer. So A, B in the outside layer. And then the most important or the most complicated one would be in the inside. So Z would be in the inside. So the middle layer Y will just be in between. Okay. Good so far?
Yep.
Okay. So let's go ahead and work on example 2, triple integral. So this integral, you have an integral that's already given. Let's take a look at this integral here. First of all, it tells us x is between 0 and y. And y is between 0 and a z. And z is between 0 and pi over 2. Based on what has been laid out over here, this is not a z simple region, right? Because z is bounded by 2 constants. Okay. I would say this is a x simple region because x is the innermost layer. Okay, x simple region. But our goal for this example is just to evaluate this integral, so we don't have to look too much look in too deep into this region. Okay, so we just need to see how do we actually calculate this integral. But the way we do it is similar. So I'll ask you guys to go ahead and use our previous methods to go ahead and from the innermost layer to the middle layer and to the outer layer. Let's go ahead and try to evaluate this integral. I'll give you guys a few minutes for the innermost layer first of all. So can you go ahead and evaluate this integral here? So 0 to y sine x plus y plus z dx. We'll come back just a minute. Okay, so this case, x is the variable, right? Y and z are just constant. So you can just think about sine, say, x plus 2. What's going to be the antiderivative? We cosine x plus y plus z. Should we have a negative sign in front of it? Yeah. Negative sign to negate it. And because it's just simple x, we don't have to divide by anything else, right? So here, x goes from 0 to y. So I'm going to plug y in for the x and plug 0 in for the x. I have negative cosine. When I throw y in, I have 2y plus z minus negative cosine. Throw 0 in, I have y plus z. So that gives us cosine y plus z minus cosine 2y plus z. Okay. That's outermost layer. And then let's go middle layer. middle layer I have 0 to z, my red box, which is cosine y plus z minus cosine 2y plus z, dy, right? dy. The y is our variable. This time it's cosine function, so antiderivative will just be sine y plus z, or cosine y plus z. And for the second part, we have sine 2y plus z. Is that it? Divide by 2. Yes, we need to adjust this 2, which would basically occur by the chain rule, right? So divide by 2. And here, y goes from 0 to z. So this is the whole thing, and value at 0 and z. So first of all, plug z in for the y. Be careful which one you're plugging, because there's y and a z. So we are plugging z in for the y. So we have sine, this is z, so I have 2z minus sine, this will be z, so 3z over 2. Subtract whichever I get when you plug 0 in for y. So this is 0, I have sine z minus 1/2. Plug 0 in, I have sine z. Are we good so far?
Yep.
And over here, we can combine sine z minus sine z over 2, right? So that's just sine 2z minus sine 3z over 2 minus 1/2 sine z. So that's the middle layer. All right, finally we got into the outer layer. Okay. So outer layer would be from 0 to pi over 2 in my blue box. So this is blue box. Sine 2z minus sine 3z over 2 minus sine z over 2. z. Okay. So we should see that. Oopsie, not here. Here. Sine 2z antiderivative will be negative cosine 2z. Don't forget to adjust by dividing by 2, right? Next one will be subtract negative cosine 3z. So it'll be positive cosine 3z. Originally divide by 2, and I also need to divide by 3. So divide by 6. Minus antiderivative of sine z would be negative cosine. So again, that turns to positive cosine z over 2. And z goes from 0 to pi over 2. So the evaluation here, we have negative cosine by throwing pi over 2 first of all. Cosine pi over 2 plus cosine 3 over 2 pi over 6 plus cosine pi over 2 over 2. Subtract. Let's plug 0 in. I have negative cosine 0. What's cosine 0, guys? Cosine 0 is 1, right? So we have a negative 1 over 2 plus, again, if you throw in 0 here, I have cosine 0, which is 1 over 6. And here we cosine 0, which is another 1/2. Okay, so inside of second open parentheses, I have negative 1/2 plus 1/2, so 1/2 got reduced. And for the first one, let's see, what do we have? Okay, negative cosine pi. Cosine pi is -1. This is -1 with a negative sign in front. So we have +1/2. So 1/2. Cosine 3/2 pi and cosine pi/2, these two both equals to 0. So we have 0 here. Okay. This is 0. This is 0. Okay. So these two items, they both equal to 0. So I just have 1/2 minus 1/6. So that's 1/3, right? So eventually I got 1/3 for this double integral. Good so far, guys?
Yep.
Okay, yeah. Let's see. Now let's quickly go back to what we just did in 3 layers. Let me see, where's my, okay. So in the first layer, we are integrating over x, right? Integrating over x. So you can see that once you finish integrating over x, what you left is only about variable y and z. So x is no longer there. And you go to middle layer, okay, middle layer, you're integrating over y. Then y is all gone after you do the evaluation, only leaving z. So it goes from 3 variables to 2 variables after the first integration, and down to 1 variable after the second integration, and down to a constant in the last integration. So the number of variables started to decrease from the innermost to middle to the outermost layers. Okay. And you will see this pattern again when you actually do the calculation yourself. All right, triple integrals. And a lot of times we are required to actually set up your triple integrals yourself, right? Set up. So this section is about how do you set up? So setting up triple integral. So when you set up triple integral, function will be easy because a lot of times it will be given, right? F of x, y, z. So integrand is easy. The question is about dv. So dv, we have said, based on different regions, you may have dx, dy, dz, or dz, dy, dx. There are 6 possibilities, because of 6 possibilities, based on how you arrange x, y, z's. If it's a z simple region, then a lot of times you go this, dz, dy, dx, or dz, dx, dy. So the question is, which one we should be looking at? Okay. So our topics next is how do we determine, how do we figure out the order of dz, dy, dx, or dz, dx, dy based on the region you're given. But anyway, no matter what, we always try to first of all determine the innermost limits, which is about your z, okay, if it happens to be z simple. And this may be a function of the outer 2 variables. Yeah, it should be a function of y or x. Then in general, we're trying to project the solid Q onto the coordinate plane of the other 2 variables, and you can determine their limits by the method used for double integrals. This sounds still pretty abstract, so let's go ahead and actually check out some questions. But in general, if it's z simple, okay, z simple, first of all, you go ahead and figure out the 2 boundaries for the z, which would be about x and y. And what's left is the limits for dy dx. So that's about the region R that we have learned before that you can represent, either using y simple or x simple region. Okay. I'm going to show you guys later how we do that. Okay. Here's one graph. Suppose this is my Q, okay, the solid region Q, not D, solid region Q. So you can tell the solid region Q, in this case, first of all, I can tell it's bounded top by this function h and bounded bottom by this function z. So for this Q, I can say z is between top function h, which is about xy, and the bottom function g of xy. Okay, so that finishes your z representation. Next will be about your x and y. For x and y, what we do is simply project this q onto xy plane. So look at it into xy plane. If you try to project it, you go down to this region R, right? So for xy, you look into region R, okay, region R. In this particular case, guys, can you tell the region R has been expressed by using a y simple expression? If you look at this region R, it is bounded below by this function and top by that function. And x has been bounded by these two constants, right?
Yep.
So the region R, y would be bounded top, which is h of x, bottom will be g of x, and x will be bounded by a and a b as the left and the right boundary. So eventually, this region in our graph can be said z is between these two functions, y is between these two functions, and x will be between these two functions. So z would be between function of two variables, which is x, y. Y would be only between a function of x, and x will be bounded by two constants. And, and then it'd be easy for you to put the limits for this triple integral. Okay. All right, so we'll see some examples just a minute of setting up the triple integral. Okay. Over next, would you like to look into the integration of 1 when the integrand, so integrand equals 1. In single integral, guys, if I do integral of ab 1 dx, what do we have?
B minus A.
Yeah, b minus a. What's b minus a? What does b minus a talks about?
Talks about the area.
Is it area?
I mean,
The length? Because x
yeah.
goes from a to b, right? So b minus a is just the length of this interval it's integrating over. So it's the length. Now in double integral, okay. Double integral, if I do double integral of 1 dA over region R. Did we talk about this before?
Yes.
We actually just talked about this last lecture, right? We said if it's double integral of 1 dA over region R, then this one just gives you area of region. So it's the area of the region. So now let's guess what happens in triple integral. Triple integral of 1 dV over solid region Q. Can you guess what this would tell you?
The volume.
Yep, so similar pattern as the double integral. So be the volume of this region. So the volume of the solid region Q. Okay. So you see the pattern goes from single integral to double integral to triple integral, right? Again,
Yep.
from length to area to volume of the region. Okay. So we have just said the volume of the solid, if it's in triple integral, we can evaluate in this format. So triple integral of 1 dV over Q, which is the volume of the region Q. Did we talk about how do we evaluate a volume by using double integral? So you may be confused. We did volume in double integral as well, right? How do we compute the volume in double integral? If it's double integral, then we do double integral of function f of xy dA over region R, right?
Mm-hmm.
So there are two ways for you to do it. You can either go double integral or you can go triple integral. And eventually, these two are actually going to be the same, because if you do this dv, let me go further. If it happens to be z simple, then you should have double integral here, and then the innermost will be about your dz, right, dz. And then whether it's dy dx or dx dy depends on the region you are given. Here is 1, and z is about a function, so 0. So be function f of x, y, g of x, y, depends on the solid. If we're just evaluating one single solid, which is completely above your xy plane, then this will be z from 0 to function f of xy plane. So if you see that, when we evaluate the innermost layer, don't we just have f of xy? Guys, when you work on this triple integral, if you go starting from the innermost layer, then the antiderivative would just be z, right?
Yep.
And z starts from 0, ends at f of xy. Then this part would just be f of xy, which is the same as here. And then dy dx, which is basically dA, differential of the area. And what's left over these two would just be the region R. This may sound abstract, but when you actually do the actual problem, you can see the similarities. So even though it looks different, triple integral and double integral, they would give you the same answer for volume of the solid. It's just a different way of setting it up. Okay. We'll have some questions about volume of solid just in a minute. Let's see. So there are two ways to represent it. You can go double integral or triple integral. Triple integral, the look is simpler than the double integral. Okay. So let's just go ahead and see this one. So volume of a solid, example 3. Consider the solid in the first octant. So first octant is like first quadrant. So x is positive, y is positive, and z is positive. Cut out from a square cylinder with sides x equals 0, x equals 1, y equals 0, y equals 1 by the plane x plus y plus z equals 4. Find its volume by a triple integral. Okay, let's go ahead and first of all sketch our graph. If you can visualize it, that'd be great. So the plane is x plus y plus z equals to 4. Okay. For this plane, it's going to be a straight plane, right? Straight plane, because it's linear. What's going to be the x-intercept? X-intercept, guys?
Would it be 1? No, it would be.
Oh, that would just be when y and z both equal 0, right? X-intercept. Yeah. So y and z could both equal 0, x which would be 4. Similarly, y-intercept will be 4, and z-intercept will be 4. So you should have 4, 4, 4 for the 3 intercepts. So the plane, oh, it won't let me sketch the big line here and here. That's going to be the plane, right? X1 plus y equals z equals 4. Good?
Yep.
And then we're going to have a solid, which is cut out from the square cylinder with sides x equals 0. What's x equals 0? X equals 0 is just the YZ plane, right?
Yep.
YZ plane. X equals 1 would be a straight plane going down here, right? So straight plane perpendicular to the XY plane. So X equals 1 is being this line here. You want to have an intersection line over here, a trace on the XY plane. Y equals 0, the trace will just be this x-axis. And y equals 1, the trace on xy plane will just be here. So y equals 1, this will be its trace. So can you sort of see the solid that will be constructed? But what it says is try to imagine you have this plane right here, right? You have plane this right here. And suppose you have a chainsaw with you. And you're going to cut this plane, okay? Cut this plane at x equals 1. So you're going to have something goes up like this, right? You're going to have the chainsaw cut at y equals 1. So it's going to cut at here. So we're going to have another line forming here. So eventually the solid would look like this kind of solid. You guys see that? That's a solid. So you cut at following the x-axis, following y equals 1. You also cut following x equals 1 and y-axis. So it will give you 4 sides, right? This is first side, and here is one side, here's another side, and the back. So left, front, right, and the back. And then it's also a top and a bottom. Is that clear?
Yes.
Okay. So we're calculating the volume of this solid as a result of you cutting the 4 sides. Okay. So we do a volume of the solid. Okay, let's call the solid Q. The solid Q will be triple integral of 1 dV over the solid Q, right? So the question is, how do we define this Q? Let's try to define this Q. Okay, let's see. The Q can be defined. First of all, let's check if Z is bounded by 2 values, 2 functions. Okay, now the quick way you can do it is, suppose you have an eye here, your eye is putting over here, and you're looking at the straight, you can looking at the solid here. So imagine you're looking at it from this end. What do you see on top and what do you see to the bottom? If you're looking at from the side, will the top be that plane and the bottom will just be the XY plane?
Yeah.
Right, okay, so the top will just be the plane, which is the plane. The bottom will just be XY plane, which is Z equals 0, right? The top is X plus Y plus Z equals 4, so that's equivalent to say Z equals 4 minus X minus Y. I'm going to say Z is smaller than or equal to 4 minus X minus Y, but greater than or equal to 0. Good so far?
Yep.
That's the first step. Okay, second step. Once you have finished Z, we don't need to look at Z anymore. We'll just need to focus on X, Y's. Okay. So what we need to look at is, now we should simply project the solid. Okay, project the solid, project the solid Q into XY plane. And let's see, what do we have? So this is a straight solid. If we project into XY plane, what we have here will just be a square, right? It looks like it's just going to be this area in the base. Okay, which X is between 0 and 1, Y is between 0 and 1. It's just going to be this area, okay, which would be our considered area, the region R. This area is very easy to represent. I can say x is between 0 and 1, y is 0 and 1. Right? This is a rectangular shape region. Good so far?
Yep.
Okay, so we have expressed all the variables, okay, z, x, and y. So we're ready to actually go ahead and set up this triple integral. So I'm going to say v of q be triple integral 1. Let's go dz first. Z is between 0 and 4 minus x minus y. And then I can either go dx dy or dy dx. Let's go dy dx. Y is between 0 and 1. X is between 0 and 1 as well. Okay, next will just be evaluation. I'm going to go the innermost layer. And this is what I say that it looks like double integral now. When you evaluate the innermost layer, your antiderivative will be z. And z will be evaluated at 0 and 4 minus x minus y. So I just have 0, 1, 0, 1, 4 minus x minus y, if you plug this for z, right, minus 0, and dy dx. Is that correct?
Yep.
Okay, does this match our definition in double integral? So it's double integral of the function f of x, y, dA.
Yes.
Right? Okay. And next, just go traditional way of computing. So go 0, 1, dx, and antiderivative with respect to y. Okay. Don't forget 4 minus x. Antiderivative will be 4 minus x, y, minus y squared over 2. And y goes from 0 to 1. Okay, so I have 0 to 1. And I plug 1 in. I have 4 minus x minus 1/2. And then I plug 0 in. I have 0, 0. Okay, so that gets us integral of 0 to 1, 7 over 2 minus x dx. Okay, so just continue here right here. That's going to be 7 over 2x minus x squared over 2. X runs from 0 to 1. It's easy to see when x equals 0, it's 0 and 0. When x equals 1, I have 7 over 2 minus 1/2. Therefore, it's 6 over 2, which is 3. So the volume will just be 3. Okay, volume will be 3. Okay, so this question is a very typical question of calculating volume of the solid by using triple integration. And during the evaluation, it will go down to double integration, which matches our previous knowledge of computing the volume by using double integration. Other than that, the calculation is pretty typical, right?
Yep.
Okay, let's do the last question here. I think we would have enough time for this. Yeah. This question, we don't need to actually evaluate it. We just need to write an iterative triple integral. Okay, iterative triple integral in the order dx, dy, dz for the volume of the tetrahedron cut from the first octant by the plane. X over 5 plus y over 8 plus z over 3 equals 1. Let's change the problem a bit. Yeah, let's just go dx, dy, dz. So first of all, let's see, what's the graph? So they were asking you to calculate the volume of the tetrahedron, right? Tetrahedron looks kind of similar to what we have there, but slightly different. Let's see. It'd be tetrahedron cut from the first octave by the plane. So this is another straight plane. Straight plane. Can we tell the x-intercept, y-intercept, and z-intercept?
Yep.
X-intercept will be 5, y-intercept will be 8, and z-intercept will be 3, right? So if you sketch it real quick, you can say x will be at 5, y will be 8, and z would be at 3. Okay, 3. So the tetrahedron will just be this whole thing. Okay, this is going to be our tetrahedron. So we're just going to set up this triple integral. So volume of this Q will be triple integral of 1 dv over Q, right?
Mm-hmm.
Now, we've seen cases that dv could be expressed as dz, dy, dx. Now they ask you to specifically write this dv in dx, dy, dz. So we should have 1 dx, dy, dz. Yeah? Oh, we'll go back there. Okay. Right, so it should be dx, dy, dz. So the question is, what do I put over here for the 3 limits? Okay. So because the x is in the innermost, so x should be bounded by 2 functions of the other 2 variables, y and z. Is that clear?
Yeah.
And y should be bounded by function of z. Okay, so I'm going to say fg function of z, h, k, right, function of z. And z should be bounded by 2 constants following their specific order. Okay, dx, dy, dz. So first of all, let's take a look at the x. Okay, x here. Here's x, y, and z, right? So in terms of the x, we can look at the x from this direction. So I should be here. And looking at the tetrahedron from the left of this xz plane. Okay, xz plane. What do you see? Try to imagine you're sitting here, you're standing here, you're looking at the tetrahedron. What's in front of you?
The zx plane.
Okay, zx plane, yes. So if your eye is here in front of you, you should have something like this, right?
Yeah.
Okay, here is your x-axis, right? X-axis. This will be the y-axis. This will be your z, right? Mm-hmm. So basically, x would be bounded by this straight line and this plane. Is that clear?
Yeah.
Okay. So my x, this straight line will just be x equals 0, right?
Mm-hmm.
Start at 0. What about this plane? This plane just comes from this equation, right?
Yeah.
It's x over 5 plus y over 8 plus z over 3 equals 1. So if you change its look, in this case, x will just be 1 minus y over 8 plus, and subtract z over 3, move these two to the right, and then multiply by 5. Is that correct? So x will be starting from 0, which is this zy plane, okay, zy plane, and ends at on the straight plane, which is oblique. So that'd be 5 minus 5 over 8y minus 5z over 3. Okay, that's your boundary of the x. So you kind of can sketch an arrow going from left to right. Make sense?
Yep.
Okay, so that finishes the first boundaries for x. Okay, next will be about the boundaries of y and z. All right, so this is about y and z. So the same thing, if we are looking at a yz only, we're going to project the solid Q onto YZ plane. Okay. So let's suppose we are projecting the solid onto YZ plane. What would you have? The solid, if you project onto YZ plane, don't you just have this rectangle on YZ plane?
Yeah.
Right, so we would have, here's Y, here's Z, and then the intercepts will be 3 and 8 respectively, right? So that's going to be what you have on the YZ plane. Let's call this region R. Is that clear?
Yep.
This region R is only in 2 dimensions, So again, you can either say this is a Y symbol or a Z symbol. Let's just go an easy way. So let's say this is Z symbol. So my Y, this Y would be bounded between 0 and 8, right?
Mm-hmm.
And your Z will start from here and at here, right? Those are the 2 intersections. So Z would start at 0, ends at the straight line, right? Straight line. Now the straight line is easy to represent as well because this is just a straight line in 2 dimensions. So I can say Z equals mx plus b, so my plus b. Good so far? What is the slope of the straight line? Slope will be negative because it's going down.
Negative
right?
3/8.
Negative 3/8. Independent variable would be y. And the z-intercept here is 3, so plus 3. So z would be between 0 and negative 3 over 8y plus 3. Okay, so eventually, I think let me just add one more slide to the end. Well, here. All right, so therefore, sorry, we'll just get one more last minute. So v here will be integral 1 dx d, did I say dy dz? Dx dy dz. Oh, sorry, dy dz. Okay, so I did dz dy, right, but you know how to do dy dz too. So if I do this, then my x will be between 0, 5 minus 5 over 8, y, minus 5z over 3, right? And my z would be between, z would be between 0 and negative 3/8 y plus 3, and y would be 0 and 8. Okay, so this is in dx, dz, dy. Sorry, we're running out of time. We should have followed the direction. It's dx, dy, dz. Next time, if we have time, we'll finish dx, dy, dz. Okay, but it's easy change. You'll just have to draw the arrow go in this direction. Okay. Sorry, guys, I'm just out of time for 1 minute. So that sort of finishes our triple integration, this section. Any questions?
And Dr. Wu, so we can calculate volume of a solid using triple or double integral, just depending on what we were given?
Yes, you can do it in both ways, whichever is easier for you. Triple integral actually can go down to double integral, right? So even though they are two different methods, but eventually they merge into the same direction.
Okay.
Yeah, that's what I'm saying. In this case, you see, start from triple integral, but go down to the double integrals. That's what we previously know, right? So you can go either way, but if the question asks you specifically saying, evaluate the volume of the solid by using a triple integral, then you'll have to start with a triple integral.
Okay, thank you.
Okay, yeah.
Yep.
Any other questions, guys? All right, if not, then we're just gonna stop here. I'm gonna see you guys on Friday. Hopefully we can finish the last section, okay? All right.